Okay, so this is something that is definitely not on the AQA specification, but it's just a little bit of fun if you find this sort of thing fun. Right, why is the bond angle here 109.5? Okay, why is it? Now with the aluminium chloride one, with the trigonal planar, that's really easy to see why, because to go around the whole thing, that's 360 degrees. You're only dealing with a flat shape, so it's much easier to visualize. All you've got to do is divide that by 3 and you've got 120. Well, how do we do it for the tetrahedral? Well, the easiest way, the way that I can understand, there are other ways, but the way I can understand is, right, let's have a cube. Right, draw a cube. Now this is a little bit of a cheat because we're jumping the gun a bit here, and I'm going to say, right, if you have a methane molecule, or if you have a regular, if you put a regular tetrahedron inside a cube, yeah, there's the center of the tetrahedron, that's our carbon. Then at the corners, you can have 2 hydrogen atoms there, and you're going to have 2 hydrogen atoms on these corners. And then you've got a regular tetrahedron described by, I draw the bonds in, okay, by those 4 hydrogens on the corners, and that will fit exactly into a cube. So what we need to do is we need to find out one of these angles, like that one there. Okay, so we're going to attempt to do that. So I'm going to say that the side of every cube is 1 unit. That makes things a bit easier. Everything is 1 unit. So I'm going to draw the diagonal in there. Now that green diagonal, by Pythagoras' theorem, you've got, that's the hypotenuse of this triangle here, isn't it? Get rid of that. So that means the green line is equal to square root of 1 squared plus 1 squared, which is of course equal to the square root of 2. So we know that that green line is root 2. Now I'm going to drop a perpendicular there in purple. So that means we know that this purple line drawn here, that's going to be half of root 2, root 2 over 2. And we know, because this carbon is right in the middle of the cube, and I'm going to draw the blue line there, that blue line is going to be 0.5. Okay, it's halfway up the cube. The cube is 1 unit high, so it's going to be 0.5. So now we can come to an angle. I'm going to draw in, draw that blue angle, let's call it theta. Okay, that's half the bond angle, isn't it? Can you see theta? It's just this little blue bit here. So we can see that the tan of theta, opposite of adjacent, well, opposite is root 2 over 2. Over the adjacent is 0.5. And of course, if you do that, that is equal to just root 2, isn't it? So on your calculator, do the tan of that. So tan root 2, that's equal to 54.73 degrees, okay? So what is our bond angle? Our bond angle is actually, 2 times theta, isn't it? Which is 2 times 54.7, which is 109.47, and there's a load of other degrees. So it's not exactly 109.5, it's 109.47. Okay, so that's how you would find out what the tetrahedral bond angle is. And then, just because this is not really an essential video at all, this is just a bit of extra. One of my students a few years ago told me he went on to do maths. He was very good at chemistry as well. if you get a sheet of A4 paper. Now A4 paper has dimensions of 1 root 2, and that's because when you fold a piece of A4 paper in half, yeah, you turn it into a piece of A5, which has got the same ratio of length to height, and then A5, then you can make A6 and so on. So you can work out that for yourself why that's got to be a ratio of 1 to root 2. And he told me if you fold a piece of A4 paper like this, so you take that corner and you fold it up to the top corner, so you'll end up with something like that. That's what it looked like. Well, this angle apparently is exactly 109.47. It's the tetrahedral bond angle, that angle there. And you can show that yourself if you want to do a little proof. You can do it. Right, that side is 1. That side is 1 unit, isn't it? So let's call this bit here where the fold is X. So that was originally the long length of the piece of paper here, that green, which I'll draw down there. And that was root 2. So that means this bit must be root 2 minus X. So then with this green triangle I'm drawing here, do Pythagoras on that, you get that 1 squared plus X squared is equal to root 2 minus X all squared. Right, if you solve that, you can really, it turns out that X, you can do that. You don't need a quadratic equation because loads of stuff cancels out. You find out that X is equal to, what is it again? Root 2 over 4. Okay, and then you've got that angle there. Let's call that theta this time. So tan theta is equal to root 2 over 4, opposite X, root 2 over 4, sorry. So there's that line there, that's X, over 1, which is the blue line there, divided by 1, which is of course just root 2 over 4. And if you do, so there's an inverse tan, theta is equal to root 2 divided by 4. (19.47 degrees). Okay, so and then what you do is you add that to your right angle there, 90. That's obviously 109.47 degrees. So that's just a bit of an oddity with a piece of A4 paper. Again, obviously not on the syllabus, but with specification syllabus, whatever you want to call it. We'll leave that there.